Welcome back. We are in lesson 12. We're going to talk about angles and diagonals and polygons and finding the measure of the interior of a polygon for just a moment. Well, maybe more than a moment. So we know that a triangle, right, has an interior degree of 180, or a total interior degree of 180. So if we were to label X, Y, Z as each of these interior angles, we could say that X plus Y plus Z is equal 180. And that would be how we would find that. It doesn't matter what X is, what Y is, or what Z is. When we add them together, they're always going to equal 180 degrees as the interior of any triangle, regardless of how you draw it. You can try all you want, pull out your protractor and measure. You're still going to get 180 degrees, regardless of what you do. We can use this truth. This is a truth. It's an axiom. We can use this truth to help us determine the interior measure of other polygons as well. So let's look at a quadrilateral. And we are going to draw a right quadrilateral just because it will help us. Notice how that all popped to 90 degrees. We know this is 90, this is 90, this is 90, and this is 90. We know that, right? And we know that 4 times 90 is going to give us 360 degrees on the interior of this quadrilateral. But we can also use this triangulating theorem here, or the rule, to help us as well. We can pick any vertex here, and we can draw a diagonal to create triangles within any polygon. And we're going to use this one just to prove the point right now. So here we have a vertex here. We're going to draw a diagonal to every vertex in this shape. So there's one already drawn here, so we don't have to draw to this vertex. We don't have one to this vertex. We're going to draw it here. And then we already have one to this vertex. So how many triangles does that make? That makes 2 triangles. And we know the interior measure of every triangle is 180. So we can say 2 times 180 is also equal to 360. So that shows in a shape that we know the degree measure of the shape, that the triangulating property works. It works for us. Or what about in some other shape? Well, first of all, let's determine what this means to us. We have 4 sides here, but we only got 2 triangles. Is it always half? Do we always get half the number of triangles that we do sides? Let's see what that means. Let's do a 5-sided shape. 1, 2, 3, 4, 5. Actually, let's do a 6-sided shape because that just happens to be what I drew. So if we have a 6-sided shape, for this one, it was half, right? So let's see if we can get 3 triangles out of this one. Since it's 6, half of that should be 3, right? So let's see if that's what works. So let's pick this vertex here. We've already got a line here. So I've got a diagonal here. I've got a diagonal here. And I've got a diagonal here. But I don't have 3 triangles. I have 1, 2, 3, 4 triangles. So what's true for both of these if I had half here and 4 here? Well, the difference is it's not dividing by 2, it's subtracting 2. So what happens is when we have a polygon, we count the number of sides. So n would represent the number of sides. We subtract 2, and we multiply that by 180. And that's going to give us the interior measure of the angles in a polygon. If I can spell polygon this morning. So n minus 2, the number of sides, where n equals the number of sides. You're going to want to write this on the back of your notebook. And this is n minus 2, where n is the number of sides, times 180 is the interior measure of the angles in a polygon. So we would say 1, 2, 3, 4. 4 times 180? Well, if we said there's 6 sides, 6 minus 2 times 180, that would be 4 times 180. So we don't have to draw the polygons. How does that help us? How does that speed us up any? Let's say we have a concave shape. For instance, here's a shape that's concave. And I'm going to draw it like this on purpose so that I can prove that it works. This is a right, all these corners are right angles. So I'm going to put my right angle where all the interior angles are 90 degrees. This is 90 degrees and this is 90 degrees, but these are exterior angles. So let's see, how many sides do I have? I have 1, 2, 3, 4, 5, 6, 7. I have 8 sides. So 8 minus 2 times 180, that's going to give us 1080, I believe. So that would be 6. 6 times 180 is 1080. Let's see if that works for us. Let's see if that's true. So I have 1, 2, 3, 4, 5 interior angles that are 90 degrees. So 5 times 90 degrees plus, now these two are exterior 90 degrees. So when we measure this exterior circle or this entire angle, the entire thing forms a circle of 360. So when we subtract that 90 degrees from that interior angle here that goes all the way around, this is going to be 270. And this is the same, so that's going to be 270 also. So it's going to be 2 times 270. When we do the math, we find this is going to be 540, and this is going to be 540, and 540 plus 540 is 1080. So you can see when given these examples that we know the measure of, we can prove that it works. So you're always going to take the number of sides minus 2 and multiply it times 180 for a concave or convex. So concave works and convex works, if I can spell convex. There you go. So concave and convex both work for that rule. All right, so let's talk about the exterior angles for just a moment. Let me clear this. So let's say we have another triangle. We know the interior measure is always going to be 180. What about the exterior measure? Well, you have 2 exterior angles at each vertex here. And you have, here's, if we extend this line down, first of all, let me say you have to begin with the premise that you're only going to count one side of the angles, depending on whether you go clockwise or counterclockwise. If you count all of them, it's going to be a different number. But we're going to do the measure of the exterior angles, and it's always going to equal 360. Why is it always equal 360? Because you're traveling in a circle all the way around, and we know that a circle is 360 degrees. So all the way around something is only 360 degrees, but we're only measuring one way. So I'm going to start here. This is me. And I'm going to walk all the way around, and I'm going to measure the exterior angle going this direction. So this angle plus this angle plus this angle. Those 3 angles are going to equal 360 degrees. How can I prove that? Right? So if you look, we have a straight angle here, right? This is a straight angle. And we know that if we had this angle plus this angle, that'd be 180. So that'd be 180, right? If we had this angle plus this angle, that's another straight angle. That'd be another 180, right? So if we had this angle plus this angle, that'd be another 180, right? Do we see how that works? But we know, and that would equal what? 180 plus 180, 3 times 180, that's 0, that's 4, that's 440. It's 440 degrees if we added all these straight angles up together. But the interior, this plus this plus this, would all equal 180. So we would have to take, if we take that interior measure away, we subtract 180 to represent the interior measures that we're taking away from this triangle. That would bring us back to 360 degrees. So can you see that? So this straight angle plus this straight angle plus this straight angle, that's 180, 180, 180. 3 times 180 is 440. But if we take away the interior measure, that leaves an exterior angle of 360. Now, this is, if you're not counting it as an exterior angle, it is a bigger angle. We know that all the way around this vertex right here, this entire circle would be 360 minus whatever's on the inside, right? We realize that. So we can also derive the entire degree of measure of the external angles by subtracting the angle from the inside as well. Just like we did when we had this shape here. And we said, well, we know this one was 90 degrees, so this had to be 270. We can derive the internal or the entire external angle of a vertex by subtracting the internal amount. Now that is not what's considered, is what is considered an external angle. The external angle is just when you walk around it, that extension on one side. It's always the side that you're going in the direction of. So if I wanted to go the other direction, let's say I decided I wanted to walk this way, then it would be this angle plus this angle plus this angle. And it'd be the same information. It's always the measure on, like on this one, that'd be 180. We know that's 180 right there, right? That one's easy peasy. But we're walking this direction now, so it's the measure, the angle on the outside. And then we have this measure here, and then we have this measure here. All right, so we can see that now. We can see how that works. But it's always to the outside of the extended line. Actually, I did that wrong. I'm sorry. This would not be that. It would be the extended line here. You can't do the external angle of a line twice. You can only do the external angle. So when I started with this one, that did this line. When I extended this one, that did this line. So all I could do, the last one, is to extend this line. So you're only extending each line one time. And that's how you do it. All right, so you have to remember that. If you walk around the other direction, then, let me get a different color, then these angles would extend this line that you're walking along. So it would be this angle, and then it would be this angle, and then it would be this angle that you're measuring. Those are the exterior angles. It has to do with the direction. So this would be this way, and the black one would be that way. It has to do with the direction that you're walking around your shape. So take care how you extend the angles whenever you walk around the shape. Okay? All right, so that is the measure of the exterior angles. Let me clear this. We've already talked about counting the triangles and the formula to do that for both concave and convex. So let me just give you a quick example problem. 12.1 wants to find the sum of the interior angles of a 7-sided shape. So 1, 2, 3, 4, 5, 6, 7, and it decides to make that a circle. Now, let me get this. 1, 2, 3, 4, 5, 6, 7. Okay, now we have a 7-sided shape. We could very easily just say 7 minus 2, let me go back to the pen, times 180. 7 minus 2 is 5 times 180, and that is going to equal 5 times 0 is 0. 5 times 18 is going to be 90. That is 900 degrees. Let's see by drawing the diagonals if we get the same number of triangles. So I'm going to pick this point. So the reason we subtract 2 is because when you have an angle, you already have two sides. You already have this side drawn, and you already have this side drawn. Those are your two sides you're subtracting. You don't have to count those. So you subtract the two angles that are already in existence, the two rays that make the angle of the vertex you're starting at. And then what you have left tells you how many triangles that makes, because you're drawing that bottom triangle or the base to make it. So you have 1 triangle, 2 triangles, 3 triangles, and then the last line creates 4 and 5 triangles. So 1, 2, 3, 4, 5. And that always works. But you have 7 sides, so technically you have 1, 2, 3, 4, 5, 6. Is that right? 1, 2, 3, 4, 5, 6. You actually have 6 diagonals, but because it's a 7-sided shape, we start with the number of sides. Counting the number of diagonals doesn't work, but the number of sides minus the 2 sides you started with of the angle works every single time. So the interior degree measure of this polygon is 900 degrees. Without us having to get a protractor and add them all up. That would be the pre-algebra way to do it, or the elementary way to do it would be to measure the angle with the protractor and then add all the angles up. This is the better way, the faster way, the easier way. That was example 12.1. That's all it was. So let's move on to the chord tangent theorem. We know a theorem is something that we can prove. That is the definition of a theorem. So in the case of a chord tangent theorem, the chord tangent theorem proves that the interior measure of an inscribed angle is half the measure of the intercepted arc. And that's that thing where we have a circle and we have an intercepted arc here, and we draw an angle. Whatever this degree of measure is, let's say that's x degrees, and this is y. Y degrees would equal x divided by 2 every single time, right? That's how that works. Here is why that works. This is an inscribed angle. And that is where y is equal to the interior angle and x is equal to the intercepted arc. So you can write this in the back of your notebook also. This is for an inscribed angle. That is the formula. y is equal to x divided by 2, where y is equal to the interior angle, and x is the intercepted arc. Here's why this is true. Let me clear this. So here we have a circle, and I am going to try to draw, right, here is the diameter of a circle, right? Let me put a little right here. Here's our center. We know that whenever we draw a tangent to a circle, that it is always at a 90-degree angle. Let me put that in the right spot. We want it just on the outside. So we know that this tangent is always going to be 90 degrees to the radius. It's always 90 degrees to the radius. That's how we determine the tangent. It's the 90-degree point. And we can always draw a radius that is 90 degrees to our tangent here, because we can shift it around wherever we want to, right? So it doesn't matter if we draw the tangent here, we can still draw a radius that's 90 degrees to it. So we always draw the radius that is 90 degrees to the tangent. That's the one we want. We know this is a 90-degree point. We also know that a diameter is a straight angle, and it intercepts the circle halfway. Half of a circle, this arc is 180 degrees, because the whole circle is 360, and the diameter cuts that in half, so we know this is 180, which means that this arc here, this is the interior or the central angle to this arc, is going to equal the same thing, right? That's 180 degrees. So this is 180 degrees. Right? Okay. So my point is, from here to here creates an inscribed angle. This tangent point to this point creates a 90 degree. 90 degrees is half of 180. So this is the inscribed angle that we create from these 2 points here. You see how that works? So this is x and this is y. Y is equal to x divided by 2. So in this case, y is 90, x is 180 divided by 2. This proves this. Now, the other thing that proves this, you can take, this is something we learned a couple lessons ago, you can take these 2 points and draw any other inscribed angle, and it's always going to give you, when you have a diameter as your chord, it's going to always give you 90 degrees. Theta, it's always going to be 90 degrees, regardless of what point. So I'm just going to pick a random point. Let's pick right here. I'm going to draw from this point to here, and I'm going to draw from this point to here. This is a 90-degree angle. So again, this is half of this, because we know this is also 90 degrees. So it proves it once again that the intercepted arc is half. It's always half of whatever. The inscribed angle is always half of the intercepted arc, and the intercepted arc here is 180. It wouldn't matter. You could draw it on this side too. In fact, let's pick a different point here, and we'll draw from here to here, and we'll draw from here to here. Still 90 degrees. Still 90 degrees. It's always going to be half of the intercepted arc. We know the intercepted arc from here to here is 180 also, because it cuts it exactly in half. So there's your proof. That's case 1. We're not going to do the other cases because they're a little bit more advanced. It just says, what if the angle is bigger or smaller than halfway, and it proves it that way as well. But that's kind of what we just did, right? It's kind of what we just did. So this is what you need to remember for an inscribed angle, where y, what we just wrote on the back of our book, that y is the interior or the inscribed angle, and x is the intercepted arc. Half of the intercepted arc is equal to y. And that is all we have for this lesson. And I will see you in lesson 13.